This is a secret message containing important information about my bank account. This is how I encoded it. Can you figure it out? In 1977, Ron Rivest, Adi Shamir, and Leonard Adelman created the RSA public key encryption code, an unbreakable code that we use to keep information on the internet safe today. Now, people have been interested in sending and keeping messages secret for centuries, including Julius Caesar. Here's an example of what's called the Caesar cipher. It is reported that Julius Caesar used what is now known as the Caesar cipher to hide secret messages, such as this one, "Attack at Dawn." The letters A, T, T, A, C, K are translated over to new letters, Y, R, R, Y, A, I, by a shifted alphabet using a code key. So the sender and receiver would have this code key and be able to send secret messages. However, if you were clever enough and intercepted this message, it would only take you about 25 tries before you could crack the code. If we want an unbreakable code, we're going to have to employ some mathematics. We're going to have to give letters their own numbers. The following is an alphanumeric code key where every letter of the alphabet is assigned a 2-digit number. 01 for A, 02 for B, etc., all the way up to Z equals to 26. Now, if we took Attack at Dawn and translated them into a string of numbers or a message block, we could then employ some mathematics to change this block of numbers into a new block of numbers, one which would be hard to crack. Here's an overview of the RSA public key encryption system. First, step 1, translate your message into a string or block of numbers. So translate A into 01, B into 02, etc. in your message. Now, the second part to this is that you want to create a modulus. The modulus we will call the number n. Now, n is the product of two very large prime numbers. We'll call these prime numbers P and Q. Now, when I mean very large prime numbers, for this to really work, you would need two prime numbers that are bigger than 100 digits long each. Now, for our purpose, to show this and to kind of get a feel for how this works, I'm going to be using some very small prime numbers, and therefore we can get across the idea. But in reality, there are really, really, really big prime numbers that are used, which makes this an unbreakable code. Next would be to create what's called the encryption key. And it's going to require us to have two numbers. One of them is the modulus that we just created from the product of the two prime numbers. And then another number E, which we'll use E for exponent. And that number E has to have satisfied two conditions. One, it's a number that's less than the number n, and it is also relatively prime to n, which just in the language of mathematics means that they have no divisors in common. Now, in order to encode and then publish this key, because once you have this key can be let out to the public, they can use it to encode anything they want. And the encoding process takes place by creating a new block of numbers, which we'll call E for the encoded message. And that takes each 2-digit block M and raises it to that number E that we have in our code key, modulo n, which is basically the remainder upon dividing by n. So E is our new message block. It's the hidden message that we can send out to the public along with our code key that we used to encode it. Now, just because someone knows how to encode this does not mean that they're going to know how to decode it. That's the difficult part. so only the receiver can decode the message. And the receiver does this by having a decoder key, similar to the encoding key. The decoder key is two numbers, again, the first one being the modulus n, and another number d, which is another type of exponent, that when I take my encoded message, each two-digit number in my encoded message, and raise it to that power of d, modulo n, the remainder upon dividing by n, we will get our old message numbers back, in which we can translate it back into letters. Now there's one other condition with this other number d, is that e times d has to be congruent to 1 modulo, and now this little weird function in there, which is lambda of n, is called the Carmichael-Quotient function. It's not something that we're going to go into any depth here, but I'll explain how you get this number in an example. So this, in a nutshell, is what makes the public key encryption system work, and that is, encoding is easy and you can tell everybody how you did it. Decoding is virtually impossible because it would rely on you knowing how to break down the number n into those two prime numbers. And factoring a big, really large number into two really large prime numbers is basically what keeps all of your information secret on the internet. So again, we're going to water this down just a little bit, and I'm going to choose two prime numbers p and q that are manageable, small enough so we can see how the result works. My code will obviously not be unbreakable, but you'll get the gist of it. Here's how it goes. So I'm going to choose the letters N and E to be the numbers 33 and 7. And so I got the number 33 by multiplying 11 times 3. Now, 7 is the exponent here, so what I'm going to do is I'm going to take each two-digit number in my message block and raise it to the 7th power. And the modulus here is 33, so then I'm going to calculate what the remainder is upon dividing that answer by 33. Are you ready for it? Here we go. 1's a pretty easy one, so we're going to start here with 20 to the 7th power. Now we get 128 followed by a couple of zeros there at the end, and I'm really just going to do some long division here with 33 to find the remainder. Now, if you haven't done long division in a long time, you keep dropping down the digits, significant digits in the dividend, and once you get to the last one, whatever you have left over after the subtraction is your remainder. So if we continue this process, and there's a lot of zeros here, so we're going to get a continuing pattern, we get a remainder of 26. So we would say that 20 to the 7th power modulo 33 is equal to 26. That's how modular arithmetic works. So the next one is 3 to the 7th power modulo 33. 3 to the 7th power is 2187, and upon dividing 2187 by 33, we get a remainder that is going to be what we put in as our E number. Okay, so again, this is remainder math. We get a 9 here, so we'll put this in as the two-digit number 09. So I'm just going to continue this process, 11 to the 7th power, 4 to the 7th power, 23 to the 7th power, and 14 to the 7th power. Now we have a new set of two-digit numbers, which we can translate our message block M into these new numbers in that sequence. So 1, 26, 26, 01, 09, 11, 01, 26, 16, 01, 23, 20 becomes our new encoded message block. And that is the unbreakable code. As long as nobody knows what the prime numbers you use to make the modulus are, you're safe. So, in coding, tell everybody how you did it, and give them the code, the secret message, and say, here, have fun. But decoding the secret message, that's where things get difficult. So here's how the decoding process works. In my case, I chose a modulus of 33 that is the product of 11 and 3. 11 and 3 are both prime numbers, so they're relatively prime to each other. Now, to find the number D in the decoding key, I'm going to have to find what's called the Carmichael-Quotient function. And it works a little bit like this. The number n is inputted into the lambda function, and we note that it is the product of 11 times 3, which is why you need to know that. And that is just the result that once you know what the product of the prime numbers is of n, you can say that the Carmichael function is going to be the least common multiple of each of those prime numbers minus 1. So here, the least common multiple of 10 and 2, 11 minus 1 and 3 minus 1, is 20. So now, e times d, our exponent from before and the new exponent in our key, must equal or have a remainder of 1 modulo this new number 20. And now since we know e was the exponent 7 from before, we want e times d, or 7 times d, to equal 1 modulo 20. Now think about it, something that has a remainder upon dividing by 20, and it's a multiple of 7. So can you think of a multiple of 7 that if you divided it by 20, the remainder would be 1? And hopefully maybe if you thought about this for a little bit, you'd come up with the fact that, 7 times 3 would give us 21. Okay, so 21 is just one more than 20, so obviously if I divide 21 by 20, I will have a remainder of 1. So d, the exponent that I need to decode this message, is equal to 3. Now, granted, that was easy enough to find. When the prime numbers are really large, that makes this number even harder to find. So computers will definitely be employed when using these really large numbers. So now that we have this decoding number d equals 3, and we also know what our modulus is, now we can show how the decoding process works. Okay, so the coding key has our modulus 33, and our decoding exponent is 3. I'm going to take the encoded message, the one that is secret, and I'm going to turn it back into the message that was known, which is m, by taking all the digits of e and raising it to the d power, raising it to the third power modulo 33. So it's the same type of process that we used for encoding, except the m and the e are sort of switched here. So here are our encoding numbers, our list or string, our message block that has been hidden. This is e, and we're going to run those digits, each of them 2 digits at a time, run them through this little equation. And each e will be raised to the third power, and found the remainder upon modulo 33, the remainder upon dividing by 33, and you'll see what we're going to get back from this is going to be all the numbers, all the 2-digit numbers that we had in the message block M, our original message. And remember, those are just the numbers that are the same thing as finding the letters when we assign numbers to letters, the alphanumeric code. So that's what M is. If anybody has an alphanumeric code, they'll be able to take the digits of M and translate it back into a message. So that's what we're uncovering now, is decoding the message gives us back the numbers in the message block M. So right now, all I'm doing is listing all the unique different digits that we have to decode, because some of them repeat in the message. And when I raise each one of them to the third power here, modulo 33, here are we get as our results. With these new numbers, we get our original message back, attack at dawn. And now the results from earlier. The secret message pertaining to my bank account says, send more money. Didn't see that one coming. Now here's a little puzzle for you. Send more money. Each distinct letter corresponds to a distinct digit from 0 to 9. The above equation can also be viewed in horizontal fashion. Write this equation in digit form.
is a logic puzzle. Good luck.